Board. Okay, so it's been a while since last Wednesday, right? Do you still remember what did we go through for this topic? Boundary layer has two boundary layers, right? Flow boundary layer and the thermal boundary layer. Okay, you know what the boundary look like, right? They're the criteria called boundary layer thickness. So you know how to calculate the boundary layer thickness. I think I gave you the equation. Okay, both both flow boundary layer thickness and the thermal boundary layer thickness. Both of them are now constant. It's gradually increasing. Okay, so that should be in your dictionary of equations. Boundary layer thickness, two thicknesses. Okay, then for the flow boundary layer, we talk about the shear, the CF, right? The shear, how to calculate the shear stress and the shear force, which is the resistance force. Sometimes people call it the drag force. Okay, the flow drag. So based on the CF, it's called skin friction coefficient, right? Or sometimes people call it resistance coefficient or friction coefficient. Okay, CF. Remember? Oh, by the way, can you see my screen?
Yes, sir.
Okay, there are two CFs if you remember. There's a lowercase CF, lowercase letter, and a capital CF. What's the difference about these two CF? Anybody still remember? That's several classes ago, right? The lowercase CF is a local skin friction coefficient. Okay, it's a local. So you can calculate the local shear stress, because I think in the first class in the boundary layer, I show you the distribution, how the change of the shear along the plate direction, right? So the shear actually decreases, okay, in the laminar region. Okay, shear is calculated by CF. CF is a dimensionless shear stress. Okay, you remember that equation for the lowercase CF? 0.664, right? Is that right? Divided by what? Anybody? Divided by square root of the local Reynolds number. Okay, at this moment you really need to be familiar with those Reynolds numbers. In boundary layer, in the flat plate, it's a local Reynolds number. At every location you have a Reynolds number. They call it Reynolds number X. Okay, so this is a local, lowercase CF. How about the capital CF? Do you remember? What does that mean? Right, that's the overall skin friction coefficient. So it's the average along the entire plate. Okay, so you can use it to calculate the overall shear force, overall drag force, which is sometimes more important to us, right? Remember these two equations? That's for the flow boundary layer. You need to know the boundary layer thickness. You also need to know the skin friction coefficient in order to calculate the shear. Okay, then in the thermal boundary layer, what do we calculate? We have a bunch of equations depending on the isothermal, isoheat flux condition, right? Nusselt number, right? Nusselt number, local Nusselt number, or let's say average Nusselt number or local Nusselt number, right? What is the Nusselt number for? Anybody? Come on, walk with me. Let's learn it. Learn the stuff in the class. It's important to you. Okay. I don't want you to spend too much time after class. Let's do some experiment, have some fun, have some hands-on experience. But in the class, I want you to fully understand the knowledge, the content, the theory, okay, to save you time. So what is a Nusselt number? Anybody?
You use it to find the local heat transfer coefficient?
You find the heat transfer coefficient as well as the average heat transfer coefficient. They are the same thing, okay? One is dimensionless and one is dimensional. Oh, I need to admit somebody coming. Hold on, let me turn on my waiting room. Okay, I have 23 students now. Okay, good. Same thing here. Okay, it relates to the local shear stress and the average shear stress. Okay, so These are the pairs. You really need to remember. You have so many equations, so you have to remember what are these variables for, what the meaning of those variables. Then in the iso heat flux condition, so you can calculate the average water temperature, right? It's isothermal and iso heat flux condition. Okay, so in that sense, you can also calculate the Nusselt number and heat transfer coefficient. Okay, so this is a big picture. Okay, so far those information we introduced. So what is Reynolds analogy? That's a very famous one. If you don't know Reynolds analogy, if you say you had a heat transfer class, people will laugh at you. Okay, that's very important. Actually, that's the full name, Reynolds-Coburn analogy. So we call it the Reynolds, Reynolds-Coburn, there are two names, analogy. Okay, but usually people just call it the Reynolds analogy. The meaning of the Reynolds analogy is to relate. You see, you have two separate boundary layers, flow and heat transfer, right? The Reynolds analogy is to relate the flow boundary layer with heat transfer boundary layer. That's a bridge between the two of them. Okay, so the equation is this. I will introduce a new number called Stanton number. Okay, Stanton number times Prandtl number to the power of 2/3 equals CF, capital CF over 2. Okay, that's a famous one. So that related, you see in the left-hand side of the equation is actually the heat transfer. Right-hand side of the equation is the shear, is the resistance, is the friction. Okay, so they have the equal sign, so they are related. What is the Stanton number? So this equation can be local or can be average, capital. Then this can be average, okay? It's okay, but for local and for average, it looks the same equation, okay? So Stanton number is defined as this. Heat transfer coefficient divided by rho, divided by Cp, divided by velocity, free stream velocity. So if it's average Stanton number, there will be average heat transfer coefficient, okay? So local and average share the same form. So now you know, okay, that makes sense. In the left-hand side, the heat transfer coefficient, see? It's a heat transfer coefficient here in the left-hand side of this Reynolds analogy equation. And the Prandtl number is related to the heat transfer too, right? Right-hand side is the friction, okay? So the friction and the heat transfer is related. Basically, that's Reynolds analogy, okay? So in other words, if you know heat transfer coefficient, you can actually predict the friction. How wonderful is that, right? Or vice versa. If you know the friction, skin friction coefficient, you can predict the heat transfer coefficient based on the Reynolds analogy. Okay, that's for laminar flow. For turbulence, there will be a set of a new equation, but this is the laminar, okay? So that's pretty powerful, actually pretty good to use. Okay. Did everybody follow me on this? Is that clear enough? Okay, so the best way to learn is doing a problem. Okay, so this, if you don't have any problem with this, if it's easy to understand, let's do a example problem. This is our next quiz. Okay, it's a 10-point quiz now. Okay, let me send you the problem. I want you to calculate a skin friction coefficient and the shear force, shear stress, then calculate heat transfer, total heat transfer. I want you to go through that process, okay? Let me send you, I want you, everybody turn on the video if you can, okay? In other class, some people, I did a quiz, you know, people doing some, something not good, okay? I wanna see you guys when I give a quiz. So turn on the video, please, if you can, okay? And let me send you the problem statement through GroupMe, okay? Then let me explain to you, okay? So don't worry, we have plenty of time for this problem. This is a learning process. It's not really, don't worry about it too much, okay? But I want you to, everybody, go through that problem with me. So that's a goal. Okay, Actually, I made it up, this problem. This problem is starting from example 5.3. We talked about it in class. Example 5.3, right? I'm sending you the problem statement, but I don't want you to calculate what exactly the 5.3 wants you to calculate, okay? I want you to calculate the skin friction coefficient, okay? I will write it in the text. So 1, capital CF, okay? 2, shear stress. Okay, I'm writing, so don't worry. I'll send it to you all together. 3, shear force. Okay. 4, average heat transfer coefficient. Okay. 5, the total heat transfer. Total heat loss. Okay, so these are 5 questions. That's why it's a 10-point quiz problem, a lot of questions. But you see, these questions, one step by one step, it's give you steps, okay, to calculate the overall heat loss. Okay, so it's actually straightforward. Just follow what we learned here. Do you still remember how to calculate the shear stress and shear force based on the CF, capital CF? Okay, this is the shear stress, and the shear force will be tau times surface area. Okay, this is all the information you need. Then let me give you the properties. Okay, let me send you the properties. Let's do this as a practice. Really, this is a good practice for you. So after this, you will be good on doing this topic. Okay, I'm sending you the practice. Sending you the properties. Okay, let me see. Did everybody turn on the video? Okay, I still see several of you not turning on the video. Please turn it on if you can. Okay, right. Bring a paper. I want you to write on your paper, then submit it through Moodle. I will open the Moodle submission site shortly. Okay, but don't worry about the time. Let's do it like 15 minutes. Okay, 15 minutes should be more than enough for this problem. Just go step by step. I ask 5 questions. Basically, these are the 5 steps to solve this problem. Okay, do one by one. Okay. Please walk alone, walk on your own. Okay, you should do well. Okay, I believe in you. You don't need to.
Can you put your share screen back up so I can get the equations for shear force and shear stress?
Okay, let me give you, yeah. Okay, do you see it? Okay, I can keep this on. I can still see your video. It's okay. I keep this on. Okay, so these are the equations we learned today. Reynolds analogy, right? 2 equations we introduced here. So that's the process I want you to go through. Okay. Eventually to find out the total heat transfer rate or total heat loss from the surface. Okay. Any question you can jump in. Yeah, maybe I can answer. Now I'm going to open the Moodle, okay, submission from Moodle. So after you finish, you can just take a picture of your writing and post it in Moodle.
Which CF do you want again? The overall or local?
It's a capital CF. I put it on the question statement. Capital CF. Well, it help you because I want you to calculate the overall frictional force, right? So that should be the overall friction coefficient. Okay. By doing this problem, I hope you fully understand these variables, these letters. Okay, these things. That's the goal. Okay.
Where can I go to find the chart for the PR number?
0.7. Did I
Thanks.
give it to you? I did. If I didn't, then it's 0.71. It's air.
Okay, thank you.
You're welcome. Okay, it's there. Did you see that PR number? The Prandtl number 0.7.
I'm seeing the second picture now.
Yeah, yeah. Okay, I made the deadline due is 11:35. I give you way more than, let me see. What time is it now? 11:21. So I still give him more than 15 minutes. Okay, so. Again, if you can hear me, please turn on your video if you can. Just want to be fair to everybody. Most of you turn on the video. So this problem, I'm asking to calculate the overall, right? So it's 40 centimeter long, okay? Not in the middle. I don't care in the middle.
So are we supposed to know the area of the plate?
Area is the unit. The z direction is unit length. That's the problem statement says.
Oh, okay.
So,
I see the
One.
very bottom.
yeah,
Yeah,
yeah.
okay.
Okay, I have seen none submission yet. It's 11:33. Okay, seems like you need more time, right? Let's make it to 11:40. So. Okay, 11:40 is our final time. No more postpone. I need to explain the result and talk about it. So I need 5-10 minutes. Okay.
What time do we have till?
2 more minutes. So 2 more minutes, 11:40, please submit whatever you have. Okay, so I need to I need to have the last 10 minutes to give you the answer.
Is it going on GroupMe?
Please submit to Moodle first if you can. Okay, Moodle is easier for me to keep record. Then if you have trouble, then GroupMe. I will have a lot of long list in the GroupMe, so sometimes it's difficult for me to find. Let's see how many I received. I received 6 so far. Okay, if Moodle is closed, I don't want to change the time anymore. If Moodle is closed, you just send me to the GroupMe. Okay, 11:40 now. Please send it now. Yeah, I received 3 on my text. After I start to talk about it, I won't accept anymore. Okay. Okay, I got 7 from Moodle, 4 from the text.
We get 2 drop quizzes, right, sir?
Oh yeah, you can do job quizzes. So don't worry about it. Come on, give me some time to talk about it. Just submit. Okay. Well, that problem, I made it up myself, but I feel if you can do it in 15 minutes for that problem, you're good on this topic. You can start to work. If people hire you to do some work like this, go ahead. Okay, you have the basic knowledge. That's good. 2, 3, 4, 5, 6, 7. 7 plus 7, I got 14 only. Okay, where are the others? 2, 3, 4, 5, 6, 7, 8. Well, I'm here teaching this class. I need to have some quality control, right? Our graduates, you should do the work. Should be able to do the work. Okay, that's my goal. Okay. I'm going to stop accepting anything. Final minutes, seriously. So far, I received 15 total. Okay. I guess I have to start. Okay, that's it. If you haven't submit, probably you don't need to. Maybe that's your job quiz. Okay, so let me share my screen. Okay. Okay. I guess what's the first number you need to calculate? Let me write it to the next side of here. Okay, put on the same page. So
The Reynolds number.
What?
The Reynolds number.
Yeah, that's right. The Reynolds number. Okay. What do you got? Reynolds number for the total length. Reynolds number L, right? What do you got?
I got 43,243.24.
Okay, that's close. Okay, I got a 46,082. Okay, so that's the first one. So because the capital CF, you needed the Reynolds number. So based on that, what is your what do you say?
Can you show us how you did that?
Oh, okay. So you have to use the velocity, which is 2 times 0.4. That's the length of the plate, divided by viscosity is 17.1 17.36 by 10 to the negative 6. Okay, that's how you get this Reynolds number. The property is given, right? Viscosity is given, 17.36 times 10 to the negative 6.
Dr. Sang,
Yep.
maybe I'm blind. I just remember reading in the problem statement that the viscosity was 1.85 times 10 to the negative 5th in the problem.
Well,
that you sent us.
but I sent you the property table.
Oh,
Okay, for the
I see
second,
that
but it's
now.
okay. It's no big deal. If the problem did say that, let me double check. Okay.
Yeah, that's what I did as well. I did it off the
That-
problems.
Okay, so you use that 1.85. That's fine. No big deal. If that's the property difference, I don't care. Okay, so 43,000 it should be good too. Okay, if that's the case. So based on this, CF will be what? Anybody? It should be close, right?
Quick
Even
question,
with
Dr. Sang.
what?
Do we not multiply by row or anything on the REL or no?
Reynolds number, you mean? Depend on which viscosity you're using. This is the kinematic viscosity. If you use dynamic viscosity mu, then you have to have a rho in the top.
Okay, got you, sir.
Okay, yeah. Be careful. That's the point. You see, I want you to practice this. Exactly the point, how much quiz point, it's not that important. But actually, I want to go through this. You will see the problems when you go through it, okay? Sometimes people forget which viscosity or this kind of things, okay? So the capital CF, anybody? Whatever your value should be close to mine.
I got 0.00319.
I got 3.06 times 10 to the negative, no, I'm sorry, 6.12 times 10 to the negative 3. Okay, based on this calculation, okay. Then what's the next question? Shear stress, right? Is that what we do? Next question?
What'd you do to find your CF? What did you do? Did you do 0.664 divided by, or did you
No,
do
this one.
1.33?
1.33.
Okay.
That's the overall capital CF. See, I said the capital CF. That's overall. There are two. Again, see, when you do this, you notice some error, right? When you some mistakes.
4.33, not 1.33.
Yeah, 1.33.
Okay, you had said 4, so I was confused.
1.33. I think that equation given to you before. Okay, early a couple classes ago. Okay, so when you do this process, you will see, okay, what kind of error, capital CF or lowercase CF. Okay, be careful. I emphasize it in the beginning of class. Lowercase CF is a local skin friction coefficient. It's just a local value. Every point, every location, you will have a shear stress. You will have a local shear coefficient. Okay. But we are talking about overall, okay, capital. So pick the correct equation. So now shear stress, what is shear stress? Times half rho u squared, right? Is that right? Shear stress, what I got is 0.0136 Newton per meter square. Okay, so how about shear force? Overall shear force is shear stress times area multiplied by 0.4, right? 0.4 meter long. So it will be 0.055-ish. Okay, 0.4444. Yeah, Newton. Okay, what's the next question? Average H, which equation you are going to use for average H? See, Reynolds analogy, right? You need to find your Stanton number. So in this problem, the Stanton number based on the half of capital CF will be, average Stanton number is 3.88 times 10 to the negative 3. Okay. Right. So then come back to the H. Your average H will be what? Will be 8.698. Okay, 8.698 Newton per meter square C. Okay. Then it's your overall heat transfer loss. Q will be HA delta T. Okay. So what is the total loss? It's 114.8 watt. Okay, so this is a process of solving a heat transfer problem through a flat plate. Okay, so any questions? I want you to have a clear picture of the process of solving this type of problem. So if you know how to solve this, just like I said, if you can solve this problem in 20 minutes, you're good on this topic. People hire you, you can start to work on those problems. Okay. I guess that's it for today.
Dr. Zhang.
Yes, yes.
Yeah. How did you get this shear stress?
Shear stress is half rho u square. See, I told you the equation here. Half rho u square CF. Okay, so okay, you have to be really familiar with this set of equations. That's why in heat transfer class, I emphasized many times, you probably need to memorize all those equations. It's not much, okay? It's not a derivation or theory or how to derive those equations. You have those equations, you have to use them, okay? If you can memorize some of the equations, for example, shear stress, half rho u square CF, memorize it, okay? In the future career, you need to memorize those things, okay? You don't just have to open the book to find these equations. These are the fundamentals, okay? So for example, Reynolds number, okay? Those equations you probably really need to remember, okay? Stanton number, okay? Those numbers and the Reynolds analogies, okay? So that will be good for you. Your job is basically just apply those equations to do some calculation. That's it. That's all you need. Okay, for you doing the job like in the plant here, in the industry here. If you goes to the upstream research company, then it might be a different story. But if you work in the industry like here, manufacturers, that's all you need to do. Okay, you need to remember those equations and know how to apply.
I have another question, please. Yeah.
What'd you say?
I have another question. So how I use like the Nusselt number to calculate the average.
No, that's not.
age.
Did you pay attention to the class today? I'm not ask you to use Nusselt number. Don't use Nusselt. In here.
Oh, okay.
It's to use this Reynolds analogy. This is the topic today. I want you to practice using the
Yeah.
Reynolds analogy to solve the heat transfer problem. Okay. That's why you need to pay attention to my class. I want you to be in my class, have your video on, listen to every word I said, and communicate with me. Okay, that you can kind of guarantee you have a good experience and a good grade and learn good stuff. Okay. I guess that's it for today. If you don't have any more questions.
Quick question. What's our Z? Is that a 2 under the CF for the Reynolds analogy, or is that a Z?
2.
Okay.
Half. Okay. See you Wednesday.